I won. Okay, -1, Teams 0. I'm able to record. So with that very smooth start of everything, welcome Daniel to SQL Friday. This is SQL Friday number, I don't remember, 105, I think, 104 maybe. It's been a few. And thanks, Daniel, for stepping in with short notice. We had scheduled Chrissy Lemaire, who couldn't make it, but Daniel could make it, and he's going to talk about ducks and ordering them by size and name and stuff like that. I don't know really, but it's going to be something about SQL anyway. So welcome, Daniel.
Thank you.
Do your own intro, please.
I really don't know what my session is about, but it's about ducks and something about ordering your data flows. No, just kidding. Just kicking this off in case Erland or Hugo is here. This is an introductory session. This is a level 100 absolute super basic sessions, but I think most people, even seasoned professionals, will find it valuable because of sort of the mindset and how you can think of stuff. But it will contain simplifications. There will be tons of simplifications. And if you have attended Hugo's half-day session on the hash join operator, you will immediately spot some mistakes that I've made. But they're not mistakes, they're actually just simplifications. So I'm going to talk about how data is stored on a basic level, and then move on to describe how we process information in SQL queries in order to produce data flows and execution plans in SQL Server so that you get your results on screen. And the reason you want to know this is because if you just type a query, it may or may not work fine, or it may just work very, very slowly because SQL Server looks at the query and thinks it wants to handle the query differently. So whenever you're troubleshooting performance, these are the absolute basics to understand if you want to get anywhere. So for my example, we have an imaginary table in a SQL Server database. We call it dbo.ducks. Every duck has an ID, which is an integer number, a first name, a birth date, and some kind of role, because these ducks all work at a company. Yay, imaginary. So we have Daffy, who is the team lead, and because he's number one, we've designed a clustering key. So the ID number is a clustering key for this table. I'll explain what that is. But you can think of all of the data that is stored in SQL Server as stored in pages. And a page is an 8 kilobyte unit of storage. So you can think of it like this. The first row goes here, then the second row goes here, the third row goes here, and so on until the page is full. And then you start over at a new page. So holding these pages together are pointers. So every page has a pointer to the next page and to the previous page. And that way you can start off at number 1, 2, 3, 4, 5. Then you follow the pointer to the next page. You get 6, 7, 8, 9, 10, and so on. And this can be done in reverse as well. So you can start from the last page and work yourself backwards. Now, a clustered index is basically an index that defines the way your rows are stored in pages. And that means that the clustered index is the actual page in the sense that it doesn't duplicate any data. The data is actually stored in the pages in the order that the clustered index defines. So tables can exist in two forms. You can have them as a heap or as a clustered index. And a heap is just a jumbled mass of data without any particular order, whereas a clustered index is actually a tree structure that sorts your data in these pages. We're going to look a little closer at that. So here's a clustered index. You can see it going from left to right. So it's 1, 2, 3, 4, 5, 6, 7, and so on. The clustered index, as I mentioned before, is the actual table. There's no duplication in this sense. A heap, as I mentioned, is also just, imagine exactly what the name sounds like. It's a heap. If you add rows, you just drop them on top and you just build up this heap. But there's no guarantee that the rows will exist in the order you inserted them in the heap, because there might be gaps in the heap where you deleted stuff before, and SQL Server may or may not choose to fill up those gaps with new rows. You just don't know. A heap is just a heap. Like if you take all the books on your desk and just dump them on the floor, you're not sure which pages they're going to land and stuff like that. A non-clustered index is like an extra index. A non-clustered index doesn't contain the entire table. The clustered index does. So the clustered index is ordered by the key, but it contains the entire table. A non-clustered index doesn't. If you think of the phone book, for those of you who are old enough to remember phone books, the phone book is ordered by, old guy there. The phone book is ordered by your last name and then your first name, right? Whereas a non-clustered index equivalent would be like at the very, very end of the phone book. Some phone books would have reverse directories. So you could take a number and look up the number in the reverse lookup directory. And that reverse lookup directory wouldn't have the entire detail that the phone book pages had. It just pointed to a page. It says basically, this is Magnus, go check page number so and so much for his information. That's essentially what a non-clustered index is. So the non-clustered index is ordered by the index key, which is the point, and it contains the clustering key so that you can find the original record back in the clustered index if you need more information or if you need to make changes or whatever. And as I said, everything is stored in pages. The clustered index is stored in pages. A heap is stored in pages. A non-clustered index is stored in pages. Everything goes into the pages, asterisk. So if you imagine on the left, you have this clustered index. It's on the ID column, right? So it's 1, 2, 3, 4, 5, and so on. On the right, we have a non-clustered index on the first name of these ducks. So these are the same ducks that you have here, but you have only the first name and the ID being the clustering key. But the difference is here, this index page is ordered by the first name. So Angus is on top, even though he's number 10. Then is Arne, number 5, Bubba, number 11, and so on and so on. So essentially, if your query wants to view all of the ducks ordered by first name, you would be better off using this non-clustered index. But this non-clustered index doesn't contain information like birth dates and stuff. And we're going to look at that in a moment. This brings us to the concept called scans and seeks. An index seek is when you can use an index to go right to an exact item. So say you want duck number 5, you can use the clustered index, you can find duck number 5, it goes directly to that duck using this tree structure that I briefly mentioned. It doesn't have to look all over the place for duck number 5, it's just there. It's like if you order all your books in your bookshelf by author and year or title or whatever, you know exactly where to go, right? In a heap, that wouldn't happen, right? Because you don't know where in the heap duck number 5 is. You would have to look through the entire heap. So what happens here is, if you select ID and first name from ducks where ID equals 5, it does a clustered index seek. So this is the seek operator. You can see that it drills right down to the exact member that you're looking for. And in our presentation, I'm going to illustrate that with a green, yellow arrow. An index seek can also be a starting point for a scanning operation. So you can say where ID is equal to or greater than 5, it will seek to number 5, and then it will just keep going until it's done. This is called, it actually shows as an index seek in the execution plan as well, but technically it's called a range scan. Also super efficient because you can go right to the one you want and keep going. You don't have to scan through the entire table. So here's what an index seek looks like. This is our clustered index. We have a clustered index seek for ID between 5 and 10. So that means we find number 5, which is a seek, and then we just keep going to number 6, number 7, number 8, number 9, number 10. When we pass number 10, SQL Server, the seek operator knows we've passed number 10, nothing will appear because these are in order, right? These are ordered. You will know that nothing appears that is in the range 5 to 10. So we're done here. We can finish our job here. And that's what a range scan or a seek actually does. Feel free to interrupt and unmute yourself if there's any question. I love questions, and I don't want to leave you hanging for another 40 minutes or something before you're allowed to ask questions. So just fire away if there's something that's holding you up.
What's your favorite cheese, Daniel? Or
my favorite cheese?
Not that kind of maybe.
Appenzeller is probably right up there with Gruyere.
All right, thanks.
I'm Swiss, remember? So the opposite of an index seek is an index scan. If your index won't help you out in the sense that you can go directly to the member that you're looking, you have to look through the entire index or the entire table, and that's called a scan. And that's just what it sounds like. You start off at the beginning, you go through the entire data until you find whatever it is you need. Index scans are obviously not as efficient as seeks. Imagine you have a 10 gigabyte table and you want one row. So where ID equals 1, 2, 3, 4, 5, an index scan will go through these 10 gigabytes from start to finish and return anything that matches the search criteria. Whereas an index seek will just go right to the ID key that you need. Let me just, there we go. This is cheese moment.
Sorry for ruining your session, Daniel.
No, not at all. You're enriching it. So say you want to select ID and first name from ducks, and you have this clustered index and the non-clustered index. SQL Server will actually find the index that is most suitable for your query, right? The clustered index contains the entire table. It is the full width of the table fits in the is the clustered index. Whereas you could actually use the non-clustered index if all you need is ID and first name, because they both are in the non-clustered index and it's just a fraction as wide as the clustered index is. So here we have, yeah, this is an index scan, basically. We select everything, so there's no need to filter anything. We just start at the first row and we keep going. So we go here, here, here. Yeah. I need a cheese database. Yeah, and I need more time. Is there a question?
Yeah, from me. Not related to cheese, I'm sorry. Maybe you'll get into it later, but one of the things I always wonder about is how much storage an index adds to the database, especially with bigger tables. Like with 15 ducks, it's fine, but you know, sometimes you have bigger groups
for a couple of
ducks.
gigabytes, right?
Yeah. So how does that? Could you explain something about that?
Yes, and it's, this slide kind of alludes to it. If you think of the clustered index as the actual table, the full phone book, yeah. If you have a non-clustered index with just the numbers and the page where that number is featured, that index is going to be much, much smaller.
Yeah,
So
because it only refers to the right page, right? Yeah.
Exactly. So the correct answer to your question is it depends, and it depends on what you're indexing. If you're indexing a narrow column, it's going to be narrower. If you're indexing a wide column, like with lots of data, the non-clustered index is going to be bigger. Plus, and this is the thing that people forget, every non-clustered index must include the clustering key for every row. So the wider the clustering key is, the wider every non-clustered index will be as well, because it needs to point back to the original clustering key.
Yeah. I'm nodding my head that you can't see, but I am.
The size of the non-clustered index is the index columns plus the clustering index keys. That is the answer to your question.
Thank you. That is the most clear I've ever been explained this. Thank you.
Awesome.
Yeah.
Thank you. So the next up is something we call surrogability, and sarg is search argument or something, I believe. I pronounce it surrogability. It's like anything else with databases. You can pronounce it any way you like. Suppose you have an index on the ID column. This argument, this where condition, is what we call surrogable, because you can use the index to produce a range scan or a seek, right? So you can find number 5 and keep going to number 10, and you're done. This is surrogable. So this generates an index seek. What do you all think this will be? Will this be surrogable? Can I use the index to evaluate this question? SQRT means square root. You can put your answers in chat, yes or no. Will this be a surrogable query? Will I be able to use an index seek to solve this? We have an oh wait maybe. Göran says no. Göran should know better. So what happens here is SQL Server evaluates these expressions, right? And says that the root of 25 is 5, the root of 100 is 10, so we can scan from 5 to 10. The correct answer to this question is yes. How about this? How about if the power of ID to 2, to the second power, so ID times ID is between 25 and 100. Put your answers in chat. Will this be surrogable? Is this a seek? Magnus shakes his head, always the pessimist. I see a couple answers. Are you just going to say yes to everything I say because it was right the last time? Please never do this. You're correct, Els. Absolutely never do this. Because what SQL Server needs to do is it needs to scan the entire database, right? It doesn't index ID to the power of 2. It indexes ID. So what it does is it tries the first row. 1 to the power of 2 is 1, so nope. 2 to the power of 2 is 4, which is nope, nope, still no. But 5 to the power of 2 is 25, right? So that's a yes. We'll include this one. And we'll include this one, and so on. And you'd think we're done here, but SQL Server doesn't know that. It just keeps going. Maybe we'll find another number somewhere, right? It's way too complicated, but it illustrates the point that surrogability, this is going to be one of those major performance tuning issues that you will easily find in your environments. And a different way to think of this, I chose a mathematical function, but this could be a cast function. You could be casting a string to a date or a date to a string. So this is absolutely a scenario that you see in databases everywhere. This is, if you would just solve all of these surrogability issues in all databases, there would be no work for performance tuners like me or Magnus or anyone else. Cool. So table scans is basically for heaps. If you have a heap and you need to find something, it's going to be a table scan. A table scan is exactly what it sounds like. It starts at the beginning of the heap, goes through the entire heap, and returns rows that matches and nothing else. So table scans are messy. If you see these in a query plan, it means there's no clustered index for one. And there's also not a non-clustered index that could support your query. I'm going to mention key lookups as well, because you're going to see some of these. A key lookup is basically where SQL Server goes and collects one row from the clustered index. One row, and that's it. So if you need multiple rows, you're going to have to do this many times. Imagine this query, for instance. You have select ID from and first name and birth date from ducks. Remember, we had a non-clustered index on ID and first name, but it didn't include birth date. So this would generate a clustered index scan because our non-clustered index doesn't support this query. Now imagine if we add order by first name. It's really tempting. It's really tempting now to use our non-clustered index because it is ordered by first name. It's all we ever wanted. It just doesn't include the birth date, right? So what SQL Server does is it scans the non-clustered index from start to finish because we're returning all of the rows because it's ordered. We don't have to sort the data. So we get all of the rows out of the non-clustered index, but we're missing the birth date. So we're going to go do a key lookup for every single row here. This nested loop operator means for each, for those of you who are programmatic, procedural programmers. This is a for each loop. So for every row here, we're going to do a key lookup on the clustered index and collect the birth date so that we have a complete record set. Return that row, get the next row, and that row generates a key lookup and return, and so on. So here's what that looks like in our example. We're going to do a scan of this non-clustered index. We're going to pick up the birth date from number 4. We're going to move to the next one, pick up the birth date for number 1, and so on, right? So you can see how this is super efficient if you have 100 rows. It's not going to be a problem if you have 10,000 rows, unless you do it all of the time. If you have 10 million rows, this is going to be a pain. This is going to be really, really problematic. So the way to fix that is, remember the non-clustered index, it includes the index key and the clustering key. You can add more information just as included columns. And we call them included columns because it's not an index key and it's not a clustering key. You can just include more information because it's handy to have. What we can do here is we can say include birth date when we create the index. And that adds another column to the index. It's still sorted by first name. That's the only thing that we're sorting this non-clustered index on. So we're sorting the non-clustered index on the first name, but we're adding the birth date just because it's handy. And yes, this will increase the size. That's exactly correct. Otherwise, we would just include all of the columns all of the time. So for our query now, we can do, this is what it used to, this is exactly, so this is what it would look like with the included column. No need to run over to the clustered index and collect the birth date. We have it here in the table. But yes, including columns comes with a size increase because nothing is free. So any questions before I move on to some query plan operators and stuff? I will take that as a no, or that you can't find the unmute button. Either way, sometimes you need to sort data. Suppose you have this query. We select a couple of columns from Duck and we order it by the clustering key. SQL Server is kind of lazy. It already has this information sorted, so it will just collect it with a clustered index scan because we bring out all of the rows from the clustered index. And these rows are ordered. If you hover over the execution plan icon in Management Studio and you look at the very bottom, it says ordered : true. So you know that it comes ordered out of the index scan. It preserves this order. So there's no need to order this information. It's already ordered by ID, and that's why it's so practical. Suppose we order the information by first name instead. That would introduce a sort operator. And sort operators are great in one sense, but they can be a bit of a performance issue in another sense. And the reason is, here's how to think of a sort. Imagine you have a data stream. This is one of those arrows in your execution plans, right? Except I've mirrored it because you're on the other side of the camera. So the data comes from the left and moves over to the right. So this is the output, the green is the output, and the red is the input. You collect rows and you send on rows. So here come the ducks, number 2, 3, 4, 5, and so on. I'm going to take this unsorted input and just dump it out on the table here. Everything has to go out on the table. Then we sort everything, right? So we need to collect all of the rows before we can even start sorting them. And the reason is simple. We can't, or actually before we can start returning them. And the reason is simple, because the last row you get could be the first one you want to send out, right? So once we're done sorting, we can start sending them 1, 2, 3, 4, 5, 6 back to the calling, to the caller. And this brings us to an important concept to recognize when you're working in performance tuning in SQL Server. Sort is what's known as a blocking operator. So this operation here, from this point, so the data comes in, nothing comes out. Nothing comes out at this point. Nothing happens. If you're sitting here wondering, where are my rows? SQL will say, hang on, I'm sorting them. I'm still sorting. So you're stuck waiting for rows to be returned until every single data row is on the table and you're ready to start sorting. This is where you start getting the data if you're doing a select query. So this is a blocking query, and that means two things. One, it requires a lot of memory. It needs somewhere to store all of these ducks while we're actually sorting them. Ideally, it will go into RAM, into your working memory in SQL Server. And that's why more memory is usually faster. When you run out of memory, SQL Server will just stuff everything down into TempDB, and that's why your TempDB is as large as it is, and your coworker has probably put auto shrink on TempDB or something else. I can see 10 people cringing. So sorting is a blocking operation, and if you can avoid sorting, that will be beneficial to your performance. And the way, obviously, we can pre-sort the information is by putting it in an index, as we saw before. I'm going to touch on window functions as well, because they fascinate me, and I think these are like SQL 2.0. If you know T-SQL, this is sort of the next thing you want to learn. Now, imagine we want to assign a row number to a data set. So you want to select ID and first name, and then you want to have a row number which starts and is entered by the first name. So we have the ID column here just as a tiebreaker in case we have 3 people called Angus. So this is 1, 2, 3, 4, and so on. What happens here is, and this basically what happens under the hood is the same whether you're ordering by first name and ID, or if you're partitioning by first name or ID. What we're doing is we're sorting the input by these columns, by the partitioning column first and then the ordering column. Again, simplification, but outside of the scope for this. So what we need for the window function is for this input to be ordered already. And you can see that we get all of the A's here, all of the B's here, all of the C's, and so on. Because we're partitioning, or whatever we're doing, we assign a window, which is the size of the partition. And so that's what I've illustrated here. And then for every window, we set a little flag, which is called segment. The flag is called segment. So segment is like an invisible bit column. You never get to see it, but SQL Server has it internally. Segment is a 1 if this is the beginning of a new window, and a 0 if you're continuing in the same window or partition. So we have a 1 here, no change, still an A, no change, still an A. We have a B, so we set a 1. no change, no change. Here comes C, we set a 1, and so on. Now, for every segment, if we use a row number as an example, the segment means reset the counter. So here we reset the counter to 1, and for every row we increment the counter, 2, 3. Segment equals 1 means we reset the counter. And you're going to see these two operators in the query plan, and they're called segment and sequence project. Segment is this column here that we discussed, and sequence project, I think it's project or project perhaps. It makes more sense to call it project. The numbering, the ordering. So you see how beautifully this works out. Notice that no one's kept waiting, right? We can do this on the fly. We don't have to spill everything out to memory. We don't have to wait for anything. We just assign the sequence project, the segment and the row number, and send them on to output. So this is not a blocking operator. So window functions require a pre-sorted input, but they're very efficient once you have those. Here's what that looks like in SQL Server in a query plan. So for our example, partition by first name, order by ID. This will use our non-clustered index on first name, remember? It will segment, meaning we add the 1 and 0, depending on if this is the same first name as the previous row or if it's a new first name. Then the sequence project will actually generate the row number, which is a scalar value, 1, 2, 3, 4, thus compute scalar. And then we'll return everything to the caller. If we don't have a supporting index on here, SQL Server will actually sort the data, which is a blocking operator and takes time. And then it will do segment and sequence project and select. You may also have seen a new function. I'm calling it new because it's 2017 or something like that, called window aggregate, which is kind of a window function, but it doesn't require the data to be pre-sorted anymore because magic. It has to do with column store. I think.
I think magic more than.
Yeah, I think magic, actually. I don't really know what they're doing in Redmond. It's yeah. Aggregation functions are fun. Stream aggregate is the most funnest of them all because this one's not blocking because it requires a sorted input. So if you want to aggregate, you want to count how many A's, count how many B's, count how many C's, and you've already sorted by that column. You don't need to put anything in a bucket or a table or memory or anything. You can just pass them through, right? So you count, this is 1A, 2 A's, 3 A's, 4 A's, and so on, 15 A's. And then when you start at B, you realize that, okay, so we had 15 A's, and you send one row to the output and say A, 15. And then we start on B. The opposite of this, if you don't have a sorted input, or if it's too expensive to sort your input, you will see a hash aggregate. A hash aggregate is much more elaborate, and you will see hash aggregates absolutely everywhere in your environment because this is the go-to for SQL Server. This is basically what most aggregates end up doing because the real world isn't as simple and straightforward as a demo would have it. A hash aggregate actually needs to stuff all of these ducks into hash buckets. So whenever a duck comes out, we look at the key values, depending on what your aggregate columns are. And then depending on the hash value of those keys, we will put the duck in different buckets. I'm going to use the term bucket here because that's a technical term, but it comes out pretty funny here. So we put these ducks in different buckets until we've pretty much exhausted the input. Now we have them neatly arranged by A's and B's and C's. In practice, you will see A1s and A2s and A3s and B1s and B2s and B3s and so on in these buckets. But for our example, think of them as buckets. And then you can take all of the A's, we have 15 of those. You can take all of the C's, which are 7 of, and all of the B's, which are 12s. But notice what happened here. The output was not ordered by the actual key here. It's not A first and B and then C and so on. It's kind of arbitrarily ordered. So this breaks ordering. Whenever you do a hash aggregate or hash match, as it will show up in did I say mash? Oh, damn. Do you know how many years I've used this presentation and no one called it? That is amazing. I'm not even mad. That's a lot of slides.
Yeah.
Mash match. No one has seen this for like 4-5 years. I'm totally going to start saying mash match now from now on, or hash or mash hatch, whatever. So thanks, Els. And so you can't depend on this data being output in any particular order. So the ordering is broken. If you need the data to be ordered because you need a window function or something else where you have just a plain order by in your query, SQL Server will actually do the hash match first, break the ordering, and then add a sort operator, which impacts performance even more. Yeah, mash is actually an English word, I think. Hash too, I guess. Yeah. So hash match and hash aggregate break ordering. That is the takeaway. So if you do, remember we have the non-clustered index on first name. We can do select first name, count big, group by first name. It will generate a stream aggregate. This is ordered. It preserves ordering. It's very efficient. It's not blocking or anything. A select distinct will do the exact same, except you just don't count the rows. It'll generate the exact same query plan. If you do birth date, for which we don't have a supporting index, it'll just scan the clustered index, do a hash match aggregate, and this breaks the ordering. And did you also notice that the hash match is blocking? Because we need to exhaust most, if not all, of the input before we can start returning rows. So a hash match is partially blocking. So beware. Alternatively, this query could actually be represented as a stream aggregate, but you would have to sort the data first. And you can do this by all sorts of hints, but if you don't, and you shouldn't use hints unless it's for development work, SQL Server will make sort of a rough guesstimate using statistics. How many birthdays do we think are in this table? Is it worth sorting it and then stream aggregating, or is it worth just doing a hash match? And so SQL Server does a rough computation or guesstimate, really, based on the statistics, which one it thinks will be faster. And people with a lot thicker glasses than I have worked on these algorithms, so they're usually smarter than any one of us.
Though they still get it wrong, of course, because statistics is never true. So.
Exactly. Statistics can lie. Hulk vision, smash data. Yes, exactly. Smash data. I'm totally adopting that. Yeah. And if you do select distinct birth date without the aggregation function, you can also occasionally see a sort distinct sort. So note how the sort is a distinct sort. Distinct sort is like a hybrid between sort and aggregate because it will sort the data, but it will discard the duplicates while it's sorting, which is very beneficial. We don't need to keep track of how many of all of these things there are if we're not doing an aggregation function. So if we're just doing select distinct, or we're just doing group by and not using any aggregation function, we can just throw away all the duplicates and sort distinct sort will be faster for us. So any questions on these aggregates? We're going to make mashed potatoes for lunch. Yes. Lies, damn lies and statistics. That's exactly right. So joins. Joins, again, data comes from left to right, as opposed to what you're going to see in SQL Server, where it comes from right to left. A join is where you connect different data streams, and there are 3 different types of joins. The nested loop join, as I touched on before, is essentially a for each loop, right? So for each row here, you execute this query once. So here comes an A. You go and select star where ID equals A, and you send those to the output. You collect a B, select star where ID equals B, you send all of those to the output, and so on. So in a query plan that looks this way, think of this as the input. This is the top input. For each row in this, you want to do something here. In this case, we're doing a clustered index seek for each of these rows, right? And yes, it's a very contrived example, joining the table itself by its own clustering key, but you get the idea. Important to note here is you ideally want like 5 rows here and 5,000 rows here, not the other way around. All right. So you don't want to do this nested loop operation 100 million times in order to retrieve like 5 rows from this one. But the other way is fine.
Again,
Again.
a question there. If you go back to the picture, is that the actual execution plan for that query?
No comment. I made this a while back. I may or may not have included a join hint to make the optimizer do what I want, because some of these examples are really, really dumb, and the optimizer sort of catches me and says, "No, buddy, you're not."
Yeah,
that's not what we're doing today.
I would imagine that since SQL Server knows that ID is the primary key of this table, it's not going to actually do a join. It's like, I know these are the same. So
that would be neat. I don't think it's going to do that. I think, though, that it might do a merge join or something like that.
Yeah.
Which we're going to touch on now. So merge join is hands down my favorite type of join, because for those of you who drive cars, in Sweden we have something called blixtlåsprincip. In English, directly translated, you call that like a ziplock principle. So if you're merging into traffic, you let one car pass, and then it's your turn, and then one car goes behind you, and then one car from the other side. And so you get this cogwheel sort of join kind of thing, right? Or you could just do the Italian way and just drive and see what happens. Ritzen in Deutsch, in Dutch, yeah. So, so what you do with merge join, it requires both the top and the bottom input to be sorted, right? So remember the cogwheel thing, if you can see my camera. The idea is that both of these data flows need to have the same ordering. And so both top and bottom are sorted exactly the same way. So A matches A, and B matches B, and C matches C, and so on, right? And it looks basically like this in a query plan. So you have this ordered input and this ordered input, and if they're the same, you're going to get a merge join. Yeah, we call it blixtlåsprincip in Swedish, so it's pretty long in Swedish too. Hash joins, just like hash aggregates, are the go-to, right? So when SQL Server isn't able to effectively run a nested loop or a merge join, it will just default back to hash join, because hash join does everything. It just works. But the thing with hash buckets is, you remember, it requires memory. You need somewhere to actually store these hash buckets. And I'm going to preface this and say these pipes should be the other way. So the build phase is on top and the other phase is on the bottom, but it doesn't matter for this presentation. So we start by putting all of these ducks in the buckets. Then we go into the probe phase where we start collecting rows from here, and we're matching them to these buckets using the hash values, right? So that we can return it to the output. Again, hashing breaks the ordering. So we have a blocking operation which breaks ordering, just like the hash aggregate. The hash join breaks ordering, and it requires a lot of memory, and it holds up the query. Like, wait, I'm still joining all of this stuff. You need to wait. So it needs to exhaust at least one of the inputs before anything happens. This is the hash match operator. Otherwise, there's really not much to say about these. Any questions on joining?
Nope.
Awesome. Which brings me nicely to parallelism. Speaking of ordering, we usually don't really care about parallelism. Parallelism happens when SQL Server says it needs parallelism, and that'll be the end of it, right? Except if we're thinking in terms of ordered data flows, parallelism matters. And here's how it matters. Here's a single threaded flow. So think of one data flow on one processor core. You can take duck number 1, number 2, number 3, and so on. Just push them through. And they will come out in the same order that you put them in, unless you do something that breaks ordering. If you have a multi-threaded flow where multiple CPU cores do parts of the work, that partitioning, which core does which part of the work, will often break ordering. So often the partitioning that decides which CPU core does what work is a hash function. You can get a lot of different things, but hashing is typically what you see. And as we saw before, hashing breaks ordering. So you get this internally for each CPU, they are still ordered, right? So you can do ordering functions here, like window functions, merge joins, whatever. But every CPU will have a subset which is not a continuous or contiguous amount of rows. So you get 1, 2, 3, and then you get 4 on this processor and 5, and then number 6 up here and 7, and so on. Which means that once we're done with our multi-threaded work and go single-threaded again, which for instance happens when we output data to the screen, it needs to collect everything, right, to one data stream that we send back to the client. They're no longer ordered. You can't guarantee them to be ordered. So I'm not saying avoid parallelism, because there's a point to parallelism and there are valid use cases, but understand that it breaks ordering. So if you have a parallel section in the query plan, and then you need to do something like a window function or a merge join or a merge stream aggregate, which require a sorted data stream, SQL Server will have to add a sort operator, which ironically may also be parallel. So you will recognize parallel threads by the yellow arrows here. And that's basically, yeah. I have 8.5 minutes to explain to you why you should care about all this stuff and why all this is important. Why have you really been paying attention to me, or if you haven't? This is a typical SQL Server execution plan. And I want you to see this plan in a third dimension, where the third dimension is the ordering of the data. So suppose from this table, our data is ordered by schedule ID, because that's what the index does. We have a schedule, and the schedule ID is the ordering key. The stream aggregate will work on the schedule ID here. And the output of the stream aggregate, does anyone have a good guess? Will it still be ordered by a schedule ID? Use chat, or just shout out your answers. I'm used to it.
No.
Yes, it will. The stream aggregate takes a sorted input and returns a sorted output. It's non-blocking. So stream aggregate is non-blocking. It will just pass everything through, right? Now, for every schedule ID, which we've aggregated here, for each of those, because it's a nested loop, we're going to do an index seek on all of the months. right? So we're going to explode this data. For every schedule ID, we're going to explode it for a bunch of months from a lookup table. What do you folks think the ordering will be over here when we're done with this? If you think of it intuitively. So we have a stream of schedule IDs, and for every schedule ID, we're going to get a stream of months, which we presume are sorted by month. What do you suppose the ordering will be here? Yes is a valid answer. I was actually looking for the columns, which will be schedule ID and month, right? So this will be the ordering of this data stream. Now we're going to do a for each here, and the red X here in the middle means that there's no join predicate. So there's, for each of those rows, we will do all of these rows. What do you think happens here? So the primary key here is, or the clustering key or index key is report row. For every combination of schedule ID and month, we're going to get all of the report rows. This is an actual query, actually. So yeah, it does get this bad sometimes. Dramatic music playing. And Alexander is correct. Yes. So for every schedule ID and month, we get every report row, right? And because it's a for each loop, we're querying this ordered data for every row in this ordered data. And then we do a sort. We change the order to account ID and start date because SQL Server thinks that's a good idea, because that's what we're going to need going forward. Because from here on, we want to collect all of the matching transactions by account ID and start date. So essentially, for each of these account ID and start dates, we're going to do a seek on the transactions where account ID is something and accounting date is larger or something, whatever. Doesn't really matter. And we're going to aggregate and so on and so on. So this is the new output. And if you work with query plans for a while, you're going to see these kinds of orderings intuitively. And you may be able to identify bottlenecks where SQL Server does something like a sort, or if there was a hash aggregate here or something, or if there's something that's holding up your query and making it slower, you can understand it not just in terms of what operators do, but how it affects ordering and why ordering is important for all of this. Damn, I don't know how I always come in on time. It's not skill, it's just luck, really. Or lack of questions. So we have another 4 minutes for questions if there's anything I can elaborate on. Niklas? No, that was just a hand up and a hand down.
It's a wave. No, but I must be very unlucky if it's pure luck to be on time when you do your presentations.
Totally luck, Magnus. It's totally luck.
All right.
That's why I put you on the lightning talk track for Data Saturday Stockholm in May.
Yeah. I don't know why I thought I'm going to be able to build availability groups in 10 minutes and demo it, but we'll see.
I mean, time is relative, right?
Yeah.
Depends on how fast you're going. It depends on your mass, stuff like that.
Yeah.
So, yeah. I mean, if we put you on like a hypersonic rocket or something, I'd watch that presentation. See Magnus fly in like Mach 100.
The thing is, to just build availability group, it's built on containers. It's 2 minutes. But then I have to talk, and I talk slowly. So, yeah.
So it adds up, yeah. Cool. Thank you so much for having me. It's always a blast to present this session. It's always fun to be on SQL Friday. I just love the format of Lunch and Learn, and it's so valuable for people who won't or can't go to conferences all of the time. Just taking a couple of minutes out of their lunch break and just having some food and learning stuff. This applies really to all of us data people. It applies more to me than most of the audience here. I need to learn other stuff than SQL Server, and yeah.
Why?
Yeah, I trust me. Because people keep asking me about Databricks and stuff, and I'm like, I don't know. Ask someone who knows.
I haven't talked to Simon. He knows.
Yeah, exactly. So thanks so much for having me, and thank you so much to all of the attendees for being here. All my information is on the screen. If there's something I left out, just DM me on Twitter or whatever. Yeah.
Thank you, Daniel. And this is the first time you have been on this side of SQL Friday. You have been moderating a couple of times when that usually happens like an hour before I realize I can't make it. I call Daniel and say, "Can you make it?" And he can. So, and
like,
thank you.
I'm on the ski slopes. Who's going to do the SQL Friday? Yeah.
Something like that. But thanks for stepping in with relatively short notice for the presentation as well. I've seen this before, but it's I think when I saw it, I was going to present after, so I didn't really pay attention to what you were talking about. So this, I just realized they were, you were doing a presentation about cartoons or something. That was now I actually got the content as well, so that's good.
As well as the MASH matches. Thank you, Els.
Yeah, I'm gonna.
Can you imagine? I've done this presentation like 6 or 7 times, and I've never had anyone see that. So they were probably all just spaced out.
Yeah, I think this is a thing with if you do an event that is just one presentation like this, we do it once a week, and it's one presentation except for the lightning talks, but it's 1 hour. People actually do pay attention if they do join. If I go to a full day event, I'm going to be half asleep on the session after lunch, for example.
There's a lot of information. Yeah.
Yeah. So and you meet people and you get like this social fatigue, and then you sit comfortably in a chair, and the poor person who is trying to present will see like 5 pairs of closed eyes during the presentation. But so it's hard, I think, to do things in person, even though they add a level of interaction that you really can't get in a Teams call. But
yeah.
I have to go, Niklas says. Thanks, Daniel, for a very good presentation. I didn't have any question. I just pressed the wrong button. Okay.
Happens to me all the time.
Yeah.
The rules say you have to make up a question if you do. I think that was the origin of the cheese thing, actually.
It could be, yeah. What's
Yeah.
your favorite cheese? But it's a good question, though.
The PowerPoint is on my blog. If you click presentations, I think the PowerPoint should be there, and also an old recording of this session.
Oh, right. And there is going to be a new recording of this session, but probably not very soon because I'm slow. There is a deadline when I will try to do all the editing for everything that is in my backlog, and that's March 20. And Daniel.
Yeah. I think what Magnus is saying, if everyone else didn't catch it, is he's just as stressed out as I am for the MVP renewal process, and 2, he needs a faster graphic cards.
Yeah, so if anyone could get me, I don't know,
4090 maybe 4080. Is that good enough?
4090, I guess.
Mm-hmm.
I need it.
We'll start like a Venmo collection or something.
I don't know if you see, this is the computer I'm running on now. It has a 3070, but it's custom made for this computer. So it's a little bit shorter than a normal 3070. So the same goes if I buy a 4090, I have to saw off one part of it. And I'm a bit reluctant to do that with such expensive equipment.
You could start a YouTube channel if you did that. Else, yes, I will be at SQL Bits. I'm not speaking, but I'm just going to hang around on Thursday through Saturday.
I envy
So
that.
so look me up. I'm face blind. I won't recognize you, even though I've seen your profile on Twitter a couple of times. Just, you know, don't take offense. I'm just face blind.
It happens, you know.
Yeah.
I need to go back to someone is paying me for work, and I apparently need to do work as well. So what can you do?
Take care, everyone.
Thanks. I will see you soon.
Bye.
Bye.